So far, we have been able to calculate the standard cell potential. So it's that E with a zero in here, that is typically the, the, the half reaction of reduction plus the potential for the half reaction of reduction plus the potential for the half reaction of oxidation, and all of them are standard. Standard means what? Standard means a certain temperature, typically 298 Kelvin, 1 atmosphere if it's gases, and 1 molar solution if it's ions in solution or substances in general in solution. So one must be aware of what this standard cell potential is actually measuring. So what this measures is what the voltmeter is going to indicate when you put 1 molar of each of the reactants and products involved. In this case, on the left you have the oxidation of zinc that reacts with copper to give copper 0 and zinc 2 plus. Okay. So notice that both zinc and copper are solid, so copper 2 plus and zinc 2 plus, if they are at 1 molar, which they are, what this is going to indicate, the voltmeter, is going to be the standard cell potential. So in a way, the standard cell potential gives you an indication of how willing the reactants are to transfer the electrons between the reducing agent and oxidizing agent, sorry. And I say fair comparison because you need to put the same amount of the same amount of reactants and products so that you make a fair comparison. What happens if, like in a team, if to make a fair game you need to have the same players on both sides of the on both teams? What happens if you start not having 1 molar? Well, in this case you are increasing the concentration of copper 2 plus, which is a reactant, and decreasing the concentration of zinc 2 plus, which is a product. In other words, you're increasing the concentration of reactants, decreasing the concentration of products. You should think about, well, the reaction is going to move more forward. And as you well know, the relationship between NFE negative, okay, the more positive your potential is, the more negative the delta G is. So what you expect is exactly that. You have a more positive potential when you work in non-standard conditions such that you increase the concentration of reactants and decrease the concentration of products. Okay, so in this case, this voltmeter is indicating not only the tendency for reactants and products to exchange, but also indicates the difference in concentration. So Le Chatelier principle here can also be thought as a more positive potential because you have increased the concentration of reactants and decreased the concentration of products. The reaction is going to be more product favored. Okay, so let's try to describe this that should make qualitative sense into equations. As you well remember from thermodynamics, the standard Gibbs free energy depends on the enthalpy and on the entropy and the temperature. But also, we called something the instantaneous or instant change in Gibbs free energy, which is the standard, plus a component that depends on the concentration. In other words, if you are willing with 1 molar of reactants in general, see that is just 1 beaker, and you put 1 molar of reactants, 1 molar of products, if the delta G standard is negative, it means that it's going to go towards products. Okay. Now, this equation that you have seen here can be phrased in terms of potential, and that's what we're going to do now. Remember this this relationship between Gibbs free energy and electric potential. Now we can rewrite this same equation in terms of potential, and this potential is what we were able to obtain up here. This 1.17 is what you would have obtained if you plug in here the given concentrations of reactants and products, and here you put the standard one. This is a so-called Nernst equation. Nernst equation is named after a very famous German scientist, Walter Nernst, one of the founders of thermodynamics. And what you need to acknowledge here is what each of the variables is. As we said, this is the standard cell potential that you can find in tables. That does not depend on the concentration. The same way that this would be equivalent to this one. These two, the standard ones, do not depend on the concentration. You can find them on tables. R is the gas constant, T is the temperature, N is the number of electrons being exchanged, and F, as you will remember, is the Faraday constant, which is the charge of 1 mole of electrons, how many coulombs 1 mole of electrons has. So pretty much these two equations are equivalent. There's just a change of units. In this case, this is joules per mole, and this is joules per coulomb, which we usually call a volt. Okay. So nothing new other than changing the units from one equation to another. So let's try to answer a question in that regard. We are being asked to calculate the cell potential of an electrochemical cell at 298 Kelvin with these two electrodes. Okay, and we're given these concentrations. All right. We're also given the standard half reactions for the reduction and oxidation. So first, one must calculate the standard cell potential, which will be the reduction plus the standard of oxidation. So let's see in which combination will give us a positive number. That will give us the direction of electrons. Actually, in this picture we already know that magnesium is going to oxidize. It's going to be our anode. So the reduction will be our iron. So we'll leave this number as is because this is our reduction. And we will need to flip this reaction, the oxidation, so we need to change the sign. Instead of negative, it will be positive, 2.37, and this is our magnesium 2 plus. Okay, this will give 1 point, if I'm not mistaken, 1.90, let me see, it should be 92, right? Is that correct? I'll check your calculators, but it should be something around like that. Definitely positive. Okay, so the cell potential is 192, and now let's remember the Nernst equation right here. Remember there's a negative, which is different from a positive here because we are changing the units between the delta G and E. So there's a negative, and RT, we're going to work in joules, so 1 joules per mole in Kelvin at 298 Kelvin. Now, how many electrons are we exchanging? We are exchanging 2 electrons. There's a 2 in here, and then Faraday's constant is 485 coulombs per mole of electrons. Okay, and now logarithm of, and Q, as you well know, is products over reactants. My products, so it may not hurt to write the overall reaction. I'm going to write it up here. So we said that iron 2 plus is going to react with magnesium to give magnesium 2 plus and iron. Okay, notice that the concentration of solids will not be indicated in the expression for K or Q. So I'm going to have concentration of magnesium over concentration of, how about we just put the concentration, the value, concentration of magnesium up here is 0.2, or we just don't need this, molar, and concentration of iron, it's the reactant. Okay. Now let's think about if this term will be positive or negative. Well, actually, we have more products than reactants. If we have more products than reactants, by Le Chatelier, you may think that the reaction is going to go backwards, or at least backwards compared to the standard conditions. Does that make sense? Well, this ratio here is going to give something larger than 1. This means that this thing is going to be positive, but with a negative in here, something you will be subtracting 1.92, therefore your E will be negative. sorry, will be negative, will be smaller than 1.92. I'm assuming it still will be positive because this is a pretty large number, but the numbers should make sense. You should obtain a cell potential that is smaller than 1.92, because 1.92 is when you have 1 molar versus 1 molar. In this case, you are decreasing the concentration of reactants versus the concentration of products. Therefore, your potential should be smaller than the 1.92 volts. Okay, you can plug this into your calculator, but at least you should be able to understand all the quantitative aspects of this problem.